Hi, welcome to our first lesson on simple harmonic motion. So we're going to be looking at oscillatory motion just in general today and just trying to introduce ourselves to some of the vocabulary and what oscillations actually look like. So I know you've come across the term oscillation before, or you certainly should do being physicists at this level. You'll have come across it in waves when you talk about the oscillations, the waves going up and down like that, yeah. Oscillation just means something moving backwards and forwards and then back to an equilibrium point. So we've got examples of oscillations here, and I try to stick to ones that you'd be more likely to see when you're doing sort of any sort of textbook practice or exam question practice for these. So we've got the two key examples, the one with a mass and a spring system, so a spring suspended from the ceiling like that then just goes boing, boing, boing up and down. That's oscillating and then coming back to a midpoint. A pendulum, so I've drawn a grandfather clock here, but anything swinging from a big, from a fixed point with it should technically be a rigid bar, but anything swinging from a fixed point in the ceiling. There's a really nice pendulum. If you go to the Science Museum in London, they've got something called a Foucault pendulum, which allows you to sort of see the precession of the rotation of the Earth, but that's a different story. Okay, tell me your favourite pendulum in the comments below. Everyone has done twinkling a ruler to make a noise. I foolishly did not bring a ruler to the table with me, so I can't do that for you now, but feel free at home to start going boing, 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 boing with a ruler. Or a boat bobbing up and down. I thought I'd try and do at least one cartoony drawing instead of diagram type stuff. So a boat that bobs up and down in the water will be oscillatory motion as well. That's oscillating to going slightly above the water and then sinking slightly below the water. So, I've used the word there equilibrium point. So equilibrium is the point at which a system will come to rest if it's allowed to oscillate and then energy losses happen. Yeah, so if I take the example of a pendulum, let's have a point at the ceiling where it's attached from there. And then let's draw a dotted line down. So if you just have a plumb bob hanging from a point, that is going to hit or a plumb line rather, is going to come down in a straight line like that. And then that is going to be our equilibrium point here. So if I label that as equilibrium, and then we talk about the displacement of an oscillating body, and at equilibrium, displacement is 0. And then we can say the displacement is positive or negative on each side. So if I just keep it number line style and have negative there and positive here. So we're going to have our pendulum at first is going to be displaced from here. So to set it swinging, obviously you have to nudge it out of place. So let's have that as our pendulum there. Let's call this our pivot point as well, because I realise it looks the same at both ends. If it's allowed to swing, then it is first going to swing this way, and it's going to come towards the centre, and then we're going to end up with it here. Get some nice black ink smudging on my lovely purple there. And then after that, it's going to have increased in velocity all the time here. So its displacement's decreased, but its velocity's increased. And it's not just going to suddenly have 0 velocity here, so it's going to carry on swinging until suddenly, in the case of a pendulum, there's going to be work against gravity, isn't there, to eventually reduce its energy. So it's got 0, or kinetic energy, I should say. So it's now got 0 speed here, but there's a maximum negative displacement. So it's wrong to say minimum, but yeah, a maximum negative displacement. And then that's still only half a cycle, because a full cycle, much like a wave, it has to go from one point to the exact same point in the next cycle. So that's not the exact same point, that's the opposite. So this is actually only half the oscillation. So then it's going to carry on moving here, and it's going to be down here again, and then it will carry on even further, and it will go back up to here. Oh, I hope the yellow shows up. Yeah. So one cycle, one complete cycle of displacement, so let's say one complete oscillation. It's easiest for us to think about it as going from maximum displacement to 0 to, or maximum positive displacement to 0, to maximum negative displacement to 0 again, and then back to maximum positive. And that's one full oscillation. It's not just going from one side to the other. So your total displacement in an ideal world should be 0 in one whole cycle. Yeah, so it's gone from one point back to the same point again. In real life, obviously, we've got things like friction to deal with. We're not going to look at that straight away. So we're going to look at an ideal system without any friction or without any sort of energy losses to, I don't know, deforming the spring or something. And those are called free oscillations. So free oscillations have no energy losses to friction. I realise I'm doing that and the colour doesn't particularly stand out in that black. Let's have it a lovely sky blue. So no energy losses to friction. Now this this whole sequence from maximum to maximum negative to maximum again, that will take some time as well. So this is obviously happening in time. So we also have a time period for one full oscillation. And we have a frequency. Ooh, let's budge that up so I couldn't read that. And that frequency f is 1 over t. And likewise, t is 1 over f. The thing that's a little bit weirder is angular frequency. So we do have an angular frequency here, much like we did with circular motion. So our angular frequency is the same thing. Omega is 2 pi over t, which might not make a huge amount of sense in terms of angles, but actually if you think about an oscillation being a complete circle, then if you do 2 pi radians of a complete circle, that's one full cycle. Yeah. 2 pi radians in time period is one full cycle. If you go through half a cycle, that's pi radians. If you go through a quarter of a circle, that's pi by 2 radians. And it all maps to sort of going around a circle. So this whole journey here, we could also have it equally being part of a circle. That's not very circular, but if we have our maximum here, minimum here, and if we have 0 here, you can think about it going round in a circle. So let's have a go at a question. Again, one that I've done. Sadly, no exciting cartoony drawing for this one. It's just a very boring textbooky drawing of a spring and a mass. The drawing might be boring, but the physics is as fun as ever. So we've got an object suspended from the ceiling by a spring, and we displace it downwards. So we sort of nudge it down this way a little bit, and then it will start going up and down. Yeah, after that. And we're going to assume there's no losses to friction here. Not that that should matter, really, but we'll come to that in the future. And it's going to take us 9.6 seconds to undergo 20 oscillations. So, to find its time period, as it asks in question A, 9.6 seconds is 20, so one of them is going to be 9.6 divided by 20. Can't do that in my head, even though I probably should be able to, but I'm recording this in the morning and I haven't woken up yet. So 9.6 over 20 is 0.48 seconds. Then for part B, it's asking us to find its frequency. I'm going to write this here as well, just to make life easier in the future. Spoilers. Our frequency is going to be 1 over t, so 1 over 0.48, and that is, oops, 2.083 recurring. So let's call that we're only given 2 significant figures in the question, so let's call that 2.1 hertz. So the unit still hertz, or inverse seconds if you want to be awkward about it. So we're going to look now at phase difference and phase in oscillations. So you've looked at phase probably before in waves, and it's a very similar idea. So if we have here a child on a swing, so a child on a swing or a basic pendulum system, depending on how human you're feeling, this child, when we unpause time, is going to start moving towards the centre, and then there, and then there, and then there, to the beginning point again. Yeah. If we, let's play time. So, oh look at this amazing CGI animation to make him have appeared there, and this disappears. And now that has happened in, I don't know, let's make up a number. Let's say that's 0.25 seconds to keep life easy. And then at that 0. Oops, I put 0.2 because S looks like a 5. There we go. 0.25 seconds later. So at that 0.25 seconds later, an identical child on an identical swing, this child's rival from a parallel universe, has left a swing there, and he's now beginning from here. So when the other child, let's sort of, if we have this, whoops, if we have this sort of ghost child from the other version here, he's here, there's the child, inconsistent with the size of his limbs, oh well. This child is going to move forwards, and then over here, and then over here, and then over here. And in those same sort of 4-quarter cycles, this ghost child is going to move forwards, backwards, backwards, and then forwards again. So they are out of phase. So if this is 0.25 seconds for a quarter of the circle, then we've got the time period is going to be 1 second. Let's say 1.00. And we know that these are out of phase by a quarter of a full cycle. Yeah. Or you might think of it as a quarter of a wavelength, if you're thinking of path difference in waves. If it's a full cycle, we're going to say it's a quarter of a full circle, so a quarter of 2 pi. So our phase difference, which, as far as I know, there isn't any sort of nice, easy symbology for that. Symbology, is that a word? I think that's the thing that the bloke out of Da Vinci Code does, isn't it? Anyway, the phase difference here is going to be 1/4 of a circle, so 1/4 of 2 pi. So there's actually a more useful way of getting there. So that might be, actually, in general, our phase difference is going to be this 0.25 seconds divided by 1 second times that 2 pi. So this here, that's still the same as that quarter there. And it's still going to give us our final answer of pi by 2. Or pi by 2. But if we generalise that even further, we can say that our phase difference was, if we call this delta t, so the time between this cycle starting and this cycle starting, then we can say delta t is 0.25, so delta t over t times 2 pi. Or it's more likely to write it with 2 pi first, actually, just because you normally put your numbers first rather than your algebra, don't you? There we go. So, using that, I just want to extend the question we were doing a little bit earlier. This is going to be the last thing we do today. So, if we take this back, a question we did just looking at time period and frequency, and there's a reason I kept this 0.48 here, because part B of the question, if we have a second identical system that's released 0.18 seconds after the first one, so that's this 0.18 seconds is our delta t here. And we want to find the phase difference between the two of them. So, as before, our phase difference is going to be 2 pi delta t over t. So 2 pi times the fraction of the full time period that this was. So, let's plug some numbers in. 2 pi times 0.18 over 0.48. And that is going to give us, let's see if you can see everything on the screen at once, 2 pi times 0.18 over 0.48, and that gives us 3/4 pi, or 3 pi by 4, however you want to say it, depending on how mathsy or normal you're feeling. And these phase difference, because it's not a real measurement, it's only a fraction of a circle, it's okay to give these in, it's okay to leave it as pi, as a fraction of pi. You don't necessarily need to round these, weird though that feels in physics. Anyway, that's all we're going to do today. So an introduction to the vocabulary of oscillations and also looking at phase difference in real mechanical oscillations as well as waves. So yeah, hope that was okay. Please let me know how you found it, and if you've got any trouble, don't hesitate to get in touch. Thanks.